Welcome to lesson 8.1. This is our last chapter of the course, and so I hope you're ready, but we're 8.1, equations of lines in 2-space and 3-space. We're going to start by talking about equations of lines in 2-space, and do 3 examples, and then move on to 3-space. Now, we have ways of drawing lines and thinking about lines in 2-dimensional space. We have different equations for lines. We're just going to run through a couple of them right now. So we have standard form. Standard form is when you get a line in the equation form ax plus by plus c equals 0. Standard form, always set equal to 0. And how we typically would draw these is set x equals 0 in order to find your y-intercept, and then set y equal to 0 in order to find your x-intercept, and then trace your line through those 2 points. Another way that we do this is using the slope-intercept form. Slope-intercept form. This is the famous y equals mx plus b, where m is your slope and b is your y-intercept. So in order to draw this one, the y-intercept defines the place, the position of the line, and then you would start counting your rise over run to get your next point. Let's say it was 4 over 2, or well, that's not that helpful. It's like 4 over 3. You'd go up 4 over 3, and you'd have 2 points, and you draw your line. Okay? Now, what we're going to learn about today is a way to define lines in 2-dimensional space using vectors. So vectors can be used to define those lines. One of the helpful things that this standard form is also named scalar form. And the connection between this equation and our vector form is going to help us think about these lines a little bit as well. So we can also, using vectors to define lines in 2-space. Now this only works with non-vertical lines, okay? So any line that is not straight up and down, we can use a vector to define that line. And we're going to start simply by consider the line negative x plus 2y minus 10 equals 0. And the first thing that I need to do in order to determine a vector to define this line in 2-space is I'm going to get 2 vectors to work with at first. One is going to be our direction vector, and one is going to be a position vector. Okay, so let's say I'm working with any line, and I'll end up drawing the line that we're working on in a minute. But I need its direction. I need to know the direction that it's going. Well, in 2-dimensional space, the direction that a line is going is called its slope. So what I'm going to do is I'm going to convert this into slope-intercept form, and then we'll be able to get its slope. Okay, so I'm going to add x and add 10 to each side, and then I'm going to divide all of my terms by 2. So we're going to have y equals 1/2 x plus 5. Now I can see that my slope of this line is 1/2. Well, that's, remember, rise over run. So it's kind of like a change in y over the change in x. So if I wanted to represent this slope as a vector, and that would be my direction vector, I would say that as we have an x change of 2, we're going to have a y change of 1. So now this vector represents the direction of my line in 2-space. I'm just going to erase that for a second. We will draw a diagram, but I want to note that this is now called, this is the direction vector. Now, this vector does not represent the line itself, but it is parallel to the line. So this is a direction vector. It has its tail at the origin, and it goes to the point 2, 1, okay? And this vector is now parallel to this line, but we don't know the exact position of it. Now, if we think in terms of y equals mx plus b, then we know that it has its y-intercept at plus 5, okay? And it's going to be parallel to this vector. So if we go 1, 2, 3, 4, 5, it's going to look like this. This is going to cross at -10, and this is what that line is going to look like, okay? Now, to tell where this line actually is, which we know is here, we need a position vector. A position vector is any vector that has its tail at the origin and its tip touching, its tip is on the line in question. So one of the position vectors that has its tip on the line is the vector r, and we'll call it r naught because we're going to talk about more than, like obviously more than one vector could have its tip on this line, okay? So this is going to define just one piece of this line, okay? And this is the point. We're not going to do any math to figure this out. I'm just giving it to you. The vector 2, 6 has its tip on the line in question, okay? This is called a position vector. So now what do we know? Well, now we know that the line goes through the point 2, 6, and it's in the direction 2, 1, okay? So this position vector, r naught, and this direction vector, m, define this line. Now, when we talk about lines in space and we draw them on our Cartesian plane, we put 2 arrows at the end, noting that lines go forever. They are infinite in both directions throughout the plane, okay? But when we're talking about vectors, vectors have a position, a direction, sorry, and a magnitude. So this doesn't really define the magnitude of this vector. I can't really express this infinite vector. The vector is going to have a specific magnitude. And so we don't just have one position vector. We're actually going to have 2 position vectors and then find the vector length in between them. And that's going to give us our line expressed as a vector in space. Does that make sense? I'll say that again. Normally our lines go forever, but vectors don't. Vectors have a specific magnitude. So we're going to have a second direction vector, maybe something like this, and we're going to call that vector r. And then the vector in question is going to be the vector in between them, from this tip to that tip. And that's going to be our direction, that's going to be our vector in space that represents this line that has this direction. But now this point isn't enough to give us that specific vector. So we're going to figure out how r comes into play. So I know that another point on the line that can be represented by position vector r can be represented by position vector 6, 8. Okay, this is a second position vector, and this pink vector closes the triangle between r and r naught and is parallel to the vector m, our direction vector. Now let's look at the relationship between these 3 vectors, and it looks like the vector r is actually the sum of the vector r naught with this pink vector, which we're going to call the vector s. That's our displacement from here to here. So we have r is equal to r naught plus s. Let's write that down. We have r is equal to r naught plus s. Well, what else do we know? We know that vector S is parallel to vector M, which we've already learned then that vector S is a scalar multiple of vector M. It's either longer or shorter. It is some multiple of the vector M. Okay, so let's make a note of that here. We have the vector S is equal to T times M, where T is some scalar multiple of M. So what we're going to do is we're going to take this equation, and where we see that S, we're going to substitute it for T times M. So now we have the vector R is equal to R naught plus some scalar multiple of the direction vector M. This is the vector equation of a line in two-dimensional space, and we have its direction as well as its position, and we can change the length or magnitude of the vector simply by changing the parameter t. That way we can have the tip of vector r at any point along this otherwise infinite line. Okay? Now, in our specific case, how we could translate this then, if we take our vector r, vector 6, 8, 6, 8, that is now equal to vector r naught, 2, 6, plus some scalar multiple of our position vector, 2, 1. Okay, this is another form of our vector equation for a line in two space. And just to recap what we have here, you might want to do this underneath. Actually, maybe I will just erase and write these things in a more general form. So we have our vector equation in two space. We have two forms. It's vector r equals r naught plus t times our direction vector m, or we have xy, which is the vector r, is equal to x naught, y naught, which is the position vector r naught, plus some scalar multiple of our direction vector m1, m2. What has to be true here? Okay, t belongs to the set of real numbers. It's just a scalar multiple. R, which equals xy, this is our position vector. Position vector to any point along the line. And in this case, if r is over here, then it might be the unknown portion, okay? This xy might be the unknown portion, but if you have another position vector and a direction vector, then you can figure out what this position vector is. Then we have r naught, which is x naught, y naught. This is a position vector. Position vector to any point along the line. And actually, because our vectors can go any direction, they can, I could change this to r naught and r, and it would still, we'd be able to figure out what our missing vector is. So this one on the outside here, r and xy, that's always going to be our unknown, any unknown point. And this r naught, the starting position, that's going to always be our known position, our known point to any known point along the line. And the last piece we have is our direction vector, m equals m1, m2. This is a direction vector parallel to the line. Right here, parallel to our line in question. So, example 1, we're going to be doing vector equation of a line in 2 space. Vector equations in 2 space. And the first thing that we're going to do is vector equation of the line through, we're going to be giving 2 points, the point A at 1, 4, and B at 3, 1. I am going to rewrite my general forms up here at the top so I have something to refer to. R0 plus t times my direction vector m. Our other form is xy equals x0 y0 plus t times m1 m2. Okay, so when I'm going from one point to another point, I'm going to have magnitude and direction. Okay, so my first thing I'm going to do is find my direction vector. Okay, so determine direction vector. Determine direction vector. Translation, rise over run. Okay, so what I'm doing here is finding the change in y and the change in x and representing it as a vector. So in order to do that, direction vector is going to be the difference between OB. So OB is the position vector from O to B, from the origin to point B, which is represented by square bracket 3, 1. And then I'm going to work toward subtract OA, and that's going to be represented by the position vector from the origin to point A. So what does that mean? Okay, vector M then, I take first the position vector OB, which is the vector 3, 1. I'm going to subtract the position vector OA, which is the vector 1, 4. I'm going to take the difference of my x components, 3 minus 1, 2, and the difference of my y components, 1 minus 4, negative 3. Now, this is a vector, direction vector m. It has its tail at the origin and is heading to 2, negative 3. Okay, so it looks like this. Now, the line that goes through A and B is going to be parallel to this line. But where is it? I'm going to choose either A or B to be the position vector. The position vector R naught. So I'm going to go ahead and choose point B, which is going to give me the vector equation for the line in question through A and B is xy equals our position vector B, 3, 1, plus any scalar multiple of my direction vector m, which is 2, negative 3. Now, I can represent this line using any point on the line itself. Okay, we used the point B. We could also use the point A, but there's an infinite number of points on the line. So in part B, we are going to determine 3 more position vectors on the line. More position vectors on the line. All right, so we have one position vector represented here, and we have the direction. So we have a point, and then we can go in this direction infinitely, in both directions, in order to find more points. So what we're going to do is we're simply going to choose different scalar multiples for our direction vector m. I'm going to simply change the value of t, and that's going to get me from here different lengths along the line to another point along the line, which can be represented by another position vector. So I'm going to let t equal 1 to start, okay? Then what do we have? Then we have x, y equals position vector 3, 1 plus 1 times direction vector 2, negative 3. All right, well, 1 times anything is just itself, so I have 3 plus 2, and 1 plus negative 3, that's negative 2. That tells me that the position vector, 5, negative 2, also has its tip on the line in question, okay? Well, let's try another one. Let t equal, I'm just going to do 2 of them. Let t equal negative 2, then we'll have x, y is equal to, so our second position vector is going to be equal to 3, 1 plus negative 2 times our direction vector 2, negative 3. You could do this in 2 steps. I'm just going to do it in 1, but this gets distributed, negative 4, positive 6. Okay, so I'm going to have 3 minus 4, which is negative 1, and I'm going to have 1 plus 6, which is 7. And the second part of this, part B, actually asks us to draw the line that we're talking about here. So I already know that it is going to be parallel to vector m here. And I also know several points that it goes through. Okay, it goes through 1, 4. That's the point A. It also goes through 3, 1. That's the point B. And, well, I'll draw my line first. It's not going to be perfect, but not bad. I've now also found out, let me just label this point B. I've also found out that the point 5, negative 2 is on the line. 5, negative 2, making this one of our direction vectors, position vectors that hits the line. And also we did negative 1, 7. So negative 1, 7. Boom. Something like that. All right. So the red is the line AB that goes through 1, 4 and 3, 1. And the 2 blue ones that I drew there are our position vectors that also have their tip on the line. And there's an infinite number of those, clearly. C says draw a closed triangle. Draw a closed triangle that represents the vector equation using points A and B. Draw a closed triangle for the vector equation using points A and B. I'm just going to do this on the picture that I already have drawn. We're using the points A to B. We're going through A at 1, 4 and B at 3, 1. And so all I need to do then is draw my vectors, my R naught, my R, and my M. Okay, so we have the vector from O to A, or really anywhere else along this line. Okay, that is going to be my unknown R. Then I have R naught, which is going to be and we have from the point B to A. And that is our scalar multiple of our direction vector, which is represented right here. That was our direction vector. Okay, so if you can make sense of that diagram, we have a closed triangle using the the position vector OA and OB, and the direction vector M, scalar multiple of it, will close off the triangle. I'm going to clear my board to make space for example 1D. So we're using this equation that we've determined one more time, and D says determine if the point 2, 3 is on the line. Okay, so we're just determining if this line actually goes through the point 2, 3. So what we want to know is the position vector 2, 3 a defining position vector for this line that we have? And the line, I'll just pull up the equation again. We said that we're working with x, y is equal to 3, 1 plus some scalar multiple of our direction vector 2, -3. So if 2, 3 is on the line, that would mean that the position vector 2, 3 can be built from the position vector 3, 1 plus some multiple of the direction vector 2, -3. Okay? Now remember, we can think about vectors in relation to their components, their x component and their y component. So what we're saying is that if I start with 3 and I add some multiple of 2, I can arrive at the number 2. Now that's going to be true. But what has to be true in this case is that the same scalar multiple that gets me from 3 plus 2 equals 2 has to get us from 1 plus some multiple of -3 equals 3. And that value of t has to be the same value for both equations that I'm going to work with. Okay, so we're going to equate x coordinates. And we're going to see what value of t allows us to do that. And then we're going to equate y coordinates and see what value of t allows us to do that. And if they're both the same value of t at the bottom, then it works. Then 2, 3 is on the line. But if not, it isn't. Okay, so here we go. Let's take our x coordinates. We've got 2 equals 3 plus some multiple of 2. Okay, and we'd obviously write this as 2t. And now I'm just going to solve. I'm going to subtract 3 from both sides and divide both sides by 2. T equals -1/2. That is going to get 3 plus some multiple of 2 equals 2. Now our y coordinates. 3 equals 1 plus some multiple of -3. So plus -3t, or just minus 3t. Again, simple algebra. Subtract 1 from both sides. Divide both sides by -3. A t value of -2/3 is going to equate my y coordinates, but a t value of -1/2 equates the x coordinates. That is not the same value. Therefore, 2, 3 is not on the line that goes through A and B. Okay, this concept of splitting vectors into their components and equating coordinates gives us the idea of parametric equations. And it's based on it's based on exactly this idea. So it's just taking, if I rewrite this in our general term, maybe I'll do that first. So I've got, let's do it this way. X, Y equals, and this is different notes. It's not attached to example 1. It's separate notes. X, Y is equal to X naught, Y naught plus some scalar multiple of our direction vector M1, M2. So our parametric equations of a line in 2 space are, we have an x coordinate is equal to x naught plus some scalar multiple of m1, and y equals y naught plus some scalar multiple of m2. Okay, these are our parametric equations of a line in 2 space. These allow us to split up or build any position vector based on its x component and its y component, which is why it's in 2 space. And again, t has to come from the set of real numbers. So in example 2, we're going to be given a parametric equation. It is the line L1. And for a parametric equation, because it's given in 2 parts, it's given as the x component, which is going to be 3 plus 2t, and the y component, which is going to be -5 plus 4t, and here t is the same value, right? So the value of t that gets, anyway, we don't need to explain it again, but this is our parametric equation for one line. This is not 2 lines, it's one line split into its x components and y components based on the scalar multiple t, position, and direction. Here we go. We are going to find 2 points on the line. Then we are going to write a vector equation of the line, then a scalar equation of the line, and then we're going to be given another line and determine whether or not the 2 are parallel. First, to find 2 points on the line, all we need to do is pick 2 arbitrary values of t, and we'll get an x coordinate and a y coordinate of a point that is on the line. So why don't we just start with let t equal 0. Okay, if we let t equal 0, then the point P1 is just 3, -5. 3, -5. Well, let t equal 1. Then the point P2, the second point on the line, would have, or at least to find the second point, we'd have an x component that is 3 plus t times 1, and have a y coordinate of -5 plus 4 times 1. This would give us a second point of 3 plus 2 is 5. -5 plus 4 is -1. So there's our 2 points on the line, P1 and P2. And you could do this, you could find an infinite number of points on the line, just choose any multiple, any value for t. Could be a half, could be -1,000, could be a billion, anything in between, okay? B, we're going to get a vector equation for this line. Okay, so a vector equation is x, y is equal to x naught, y naught plus some multiple of our direction vector m1, m2. Okay, there's the basic form of it. And so we are going to choose either any one of the infinite number of points that we can make to be our position vector. Okay, so our position vector we could choose r naught equals 3, -5. And then we have our direction vector m. And that is actually given to us up here in the component. It's saying that x has a change of 2 when y has a change of 4. Okay, so our direction vector is actually 2, 4. So now all I need to do is give my vector equation, starting with position vector 3, -5, and adding any multiple of my direction vector 2, 4. So here's our completed vector equation. Okay, we're also going to complete a scalar equation. That's part C, and I'm just going to move off to the side here. Scalar equation. Now remember, our scalar equation is another word for standard form. So we're looking for ax plus by plus c equals 0. And one thing we did earlier is we started with a scalar equation and we isolated the t value. What we're going to do here, because we have equations with t in them, is we're actually going to, within the x component, we're going to isolate t. Within the y component, we're going to isolate t. And then since these t's are the same value, we can equate them. Okay, so what does that look like? Well, we're going to take our two equations, which is x equals 3 plus 2t, and y equals -5 plus 4t. And in each of them, I'm going to isolate t. I'm going to rewrite this in terms of t. So I'm going to subtract 3 from both sides and then divide by 2. So we're going to end up with t equals x minus 3 over 2. Over here, I'm going to add 5 to both sides and then divide by 4. So I'm going to end up with t equals y plus 5 over 4. Now I have two equations for t, and I know this t is the same as that t. So what I can do is I can equate these two. So I have x minus 3 over 2 is equal to y plus 5 over 4. Now it's a matter of simplifying and reducing, getting this into standard form. Okay, well, how am I going to do that? I'm going to just perform some basic algebra, and I'll do it in a couple steps so you can see it on your first time around. But it's really not too complicated. Whatever I do to one side, I have to do to the other side, and eventually I'm going to get everything on the same side with 0 over here, okay? So what I'm going to do is I'm actually going to first multiply both sides by 4 and by 2, okay? So I'm going to end up multiplying both sides by 8, which over here is going to give me 8 divided by 2 is 4, so I'm going to have 4 times x and 4 times -3. That's going to give me 4x minus 12. Over here, multiplying by 8 is going to give me 8 over 4 times y plus 5. That's going to give me 2 times y and 2 times 5. 2y plus 10. Now I can move these things around, add and subtract until I have everything in the right order on the left side and 0 on the right side. So I have 4x, and I'm going to subtract 2y from both sides. Then I'm going to subtract 10 from both sides. -22 equals 0. And this is not fully reduced. Running out of space here. So I'm going to divide all of my terms by 2. That leaves me with 2x minus y equals 11. Minus 11 equals 0. And this is now our scalar equation for the line in question. Up here, you could have done this in one less step. You could have said, oh, I know 4 is a multiple of 2, so I actually only have to multiply both sides by 4, and that would get you to this step a lot more quickly. But if you end up with a situation where the denominators are not factors one of the other, then you would need to multiply both sides by both of those values, which is what I did here. And last part, we're going to say is L2 given by x equals 1 plus 3t, y equals 8 plus 12t, is L2 parallel to L1. So again, how are we going to do this? Well, there needs to be some. So in part D, we're given a second line, L2, broken into its x and y components, and we're going to find out whether or not L2 is parallel to L1. What does that mean? Well, they need to have the same direction vector. Okay, they need to have the same direction component. So the direction vectors of parallel lines are scalar multiples one of another. So for instance, if we have a direction vector like this for one of them, L1 or L2, then the other one has to have a direction vector that is either this, or this, or this, or this, or this, or this, some scalar multiple of the direction vector for the other line. So what we're going to do is find the direction vector for L1. Okay, the direction vector, we're going to call it M1 for the line L1, and this is the direction vector 2, 4. Okay, now for L2, our second direction vector in question, the direction vector is 3, 12. 3, 12. So there has to be a value of t, or not t in this case, we'll use a different scalar, but there has to be a multiplier, let's call it k, that will, the same multiplier that will relate 2 to 3 needs to be able to relate 4 to 12, okay? I can tell already off the top of my head that that's not the case. To get from 2 to 3, I need to multiply by 3 over 2, or 1.5. But to get from 4 to 12, I need to multiply by 3. So these guys are not going to be parallel. But this is what it needs to look like. For L1 and L2 to be parallel, we need 2, 4 to be equal to some multiple of 312. Okay? Well, let's work this out. So for our x components, we're saying that there has to be some scalar multiple that will get 3 to equal 2. In that case, k would be 2 over 3. And for our y component, we're saying there needs to be some scalar multiple that I can multiply by 12 to get to 4. And in that case, divide both sides by 12. That's going to give me 4 over 12, which is 1/3. Okay, so here are our k values. So we can say the required k value, they're supposed to be the same if they're parallel, but they're not. The required k value does not exist. Therefore, L1 and L2 are not parallel. In example 3, we're going to be determining a scalar equation. Scalar equation, again, of a line in 2 space. And we're given the line. The line that we're given is 4x plus 5y plus 20 equals 0. First thing we're going to do is graph it. Then we're going to start thinking about a position vector that is perpendicular to that vector. So step 1, let's just graph it. There's my axes. In order to graph an equation of a line in standard form, you usually just set, rather than convert it into y equals mx plus b, you just set x equal to 0, and that will give you your y-intercept. In this case, you'll have 5y equals -20. Divide both sides by 5, you get y equals -4. 1, 2, 3, 4. And then we can set y equal to 0 in order to find our x-axis. So you get 4x plus 20 is 0. 4x equals negative 20. Divide both sides by 4. X equals negative 5. 1, 2, 3, 4, 5. Draw a straight line through 2 points. And that is our line. Again, you would note it goes through negative 4 on the y-axis and negative 5 on the x-axis. And again, if you want a little more help, let x equal 0, y will equal negative 4. And if you let y equal 0, x will equal negative 5. And that will give you the x-intercept and the y-intercept, 2 points. You can graph your line. The next thing that we're going to do is determine a position vector perpendicular to the line. So position vector perpendicular to the line. Okay, now a position vector comes from the origin. Okay, so this line is not necessarily, the vector itself is not necessarily going to cross this line, okay, unless it, extends from here backwards. But at any rate, the slope is going to be the opposite reciprocal of this slope. So the direction vector is going to cause us to be perpendicular to the line that's given. So let's figure out how to do that. Basically, we're finding first then the direction vector of the line that's given. So step 1 is find direction or determine direction vector of the line. Now, in order to determine the direction vector of the line, we're going to do the same thing we did in the 2 examples ago, I believe. 2 examples ago. We're simply going to assume or allow each of these points to be named. So we're going to have the point OA and we're going to have the point OB, okay? Or OB and OA. Doesn't really matter which way we name them. But what we're going to do then is take the difference between them, and that's going to get us our, I guess we're going to be working from left to right here. So this is going to be A and this is going to be B. And we're going to find a direction vector, the direction of this vector right here, okay? So it is, just as it was before, we're going to get OB minus, these are vectors, minus OA. All right, well, the position vector, OB, is the vector that takes us from the origin to the point given. Now, we haven't moved in this position vector. It's just the y component, really. The x component is 0. So this is going to be represented by 0, negative 4. Because we're x equals 0, y equals negative 4. That's how we found our y-intercept in the first place. And then we're going to subtract OA, which is represented by the coordinates of our y-intercept, which is 0, negative 5. 0 minus, sorry, this is, what did I do here? This is negative 5, 0. Negative 5, 0. Okay. Putting it together, finding the difference will give us our direction vector for the line. So we have 0 minus negative 5. That's 0 plus 5, which is 5. And we have negative 4 minus 0, which is negative 4. All right. That is the direction vector. So now, in order to find a vector that is perpendicular to D, we're going to let D, sorry, perpendicular to this line, we're going to let D, which equals xy, be perpendicular to the line. And then we're going to take the dot product, and we know that when two lines, or two vectors, sorry, are perpendicular to one another, the dot product is 0. So what we're looking for then is, we have the direction vector of our original line. We're going to take that dot product with our new vector, and we should get 0. Okay, so if we're taking the dot product is a product, it's a multiplication happening here. So we have our x component times our x component plus our y component times our y component. Okay, so we have 5x plus negative 4y. So I'm just going to write 5x minus 4y equals 0. So now what I'm looking for here is an x and y pair, an ordered pair that makes this statement true. Okay, I could pick a whole bunch. I could pick any number in the whole world to be x, and then find the y that makes this statement true. Okay, I'm going to do one more step that's going to allow us to find a really easy number to use, because if I express this in terms of y, okay, if I express this in terms of y, I'm going to subtract 5x from both sides, and then divide by negative 4. I'm going to end up with y equals 5 over 4x. Now, if I choose x to equal 4, then what's going to happen? The 4's are going to cancel out and y just equals 5, okay? So x equals 4 is a really easy value to use, but again, you can choose any value you want for x. It just means you're probably going to be dealing with fractions and things like that, which is fine. But this tells us that the vector d, which is perpendicular to our given line, is, I'm going to let x be 4, sub in 4 for x, that leaves me with y equals 5. This vector is perpendicular, right? That doesn't say perpendicular, perpendicular to the line. All right, and again, there are an infinite number of vectors that are perpendicular to the line. They all happen to be going, and I can draw this vector that I did draw, or that I came up with, but it's the vector d, which equals 4, 5. But I could have come up with, this vector, this vector, this vector, this vector, this vector. They're all perpendicular to the line, okay, as long as they travel along this direction. There's some scalar multiple of this direction. So something important to notice here, which it asks us to notice in part C of example 3, how does the position vector from part B, this position vector d that we just figured out that's perpendicular to our original line, how does that compare to the scalar equation? And it turns out that what happened is that the components of d, the x and y components here, correspond to the coefficients of x and y respectively from the scalar equation. So we got the equation 4x plus 5y plus 20 equals 0. And it turns out that the vector perpendicular, or a vector perpendicular to this line, is the vector 4, 5. Okay? So there's something to remember. And maybe put down in your notes, I'll jot it down. 6. The components of vector d correspond to the coefficients of x and y from the scalar equation. That also means that we could have, for instance, doubled each of these. You could take 8, 10 to be your vector, or negative 4, negative 5 to be a vector perpendicular to the original line. Any scalar multiple of 4 and 5, as long as you use the same value on each, will get you a vector perpendicular to the original line. And I'm going to go ahead and fit D here as well. D says to write a vector equation. That's equation of the line. A vector equation. So to write a vector equation, we need a position vector and a direction vector. We know Well, we actually have two position vectors. So we're back to the original line, our pink line here. So our two position vectors were OB and OA. Okay, so I can choose this vector or this vector. And our direction vector was found right here, right? M is our direction vector, 5, -4. So here's our vector equation. X comma y equals, and then a position vector, I'm going to choose the point A, -5, 0, plus some multiple t of our direction vector, 5, -4, where t belongs to the set of real numbers. All right, this example has brought up a new term that we need to learn, and it is called a normal vector. I think we've used the word normal in this way before in our math, but a normal vector to a line, it just means perpendicular, okay? So the vectors that we drew that are perpendicular to the line are normal vectors, okay? A normal vector to a line is a vector that is perpendicular to that line. So if we have a line L, that's a terrible L. If we have a line L given in standard form, ax plus by plus c equals 0, then the normal vector, which is denoted n, the normal vector n is a b. So in the example that we did, vector d is normal to the line that was given, 4x plus 5y plus 20 equals 0. Okay, so we've seen how in two-space we can represent a line a few different ways. We can give it a vector equation, a parametric equation, that's when you split it up into its x and y components, a scalar equation, or we can go into the original y equals mx plus b slope intercept form. Then the points x and y, any ordered pair that satisfies the equation is a solution to the equation, or is a point that is on the line, okay? So that should be fairly familiar. That's in two-space. Now in three-space, we can also define three-dimensional vectors using a vector equation or by parametric equations. But when we talk about a scalar equation, the scalar equation is the one that looked like standard form, like ax plus by plus c equals 0. Well, now if we're talking about that in three-space, we're going to end up having another parameter, and this will define an entire plane. Okay, a plane is the entire flat two-dimensional surface. There's an infinite number of them in three-dimensional space because you can move that plane all around any which direction, any which way, and extends forever and ever in all directions, okay? So the plane is a two-dimensional space. So in three-dimensional space, you cannot use this standard form or scalar equation in order to define a line. It will always define a plane. So we don't have to worry about that in this lesson. We'll get into that in the next lesson. But the two forms of equations that we are going to think about are the vector equation and a parametric equation. So I'm just going to make a little subheading here, lines slash vectors in three-space. And we're just going to note, just like in two-space, what do we need? We're going to need a direction vector and a position vector to a known point on the line. It's the same as in basic graphing of lines and linear equations, is you need to know a point and you need to know the direction. Okay, that's all we're saying. So we need to know the direction vector and a position vector to one point on the line. All right, so if we have a line, if we have a line passing through point P naught, and it has position vectors R naught, and it has a direction vector M, then we can find out the equation. Okay, so I'm going to write that down. The line passing through P naught with position vector R naught, which is given by X naught, Y naught, Z naught, and has direction vector, and again our direction vector M is also going to have three parameters now. I'm always tempted to call them X, Y, and Z, but our book calls it M1, M2, M3, which of course the M1 is in the X direction, M2 is in the Y direction, M3 is in the Z direction. And so if we know a position vector and the direction vector, then the vector equation is the vector equation is, and I put vector equation on a new line because I'm also going to write underneath this, do a parametric equation. So it has two forms. The first is R is equal to R naught plus some multiple of our direction vector, where t belongs to a set of real numbers. Or we could write this as a vector equation in this form: x, y, z is a vector that has position vector x naught, y naught, z naught, and some multiple of our direction vector m1, m2, m3. Again, where t belongs to the set of real numbers. Now, parametric equation, so this is a vector equation. The vector equation is the parametric equation is, and again, now we're going to be splitting it instead of just into its xy components, we're going to be splitting it into its xyz components. So we've got x equals x naught plus some multiple of m1. You got y equals y naught plus some multiple of m2, and you've got z equals z naught plus some multiple of m3, and that is going to be the line. And t is the same in each of these breakups here, okay? And we note also that t belongs to a set of real numbers. All right, so these are our tools for the last example. And I'm going to see if I can just leave them up there if we have enough space. So example 4, equations of lines in 3 space. Step 1, we are told a line passes through A, which is given by the point 2, -1, 5, and it passes through B, which is 3, 6, negative 4. We're going to write a vector equation first. We're going to write a vector equation, then a parametric equation, and then we're going to determine if a given point is on the line or not. Okay, so step 1 for vector equation is the same as before. We are going to find a direction vector. So our direction vector is the vector that gets us from the tip of OB to the tip of OA. We have these vectors here. So OB is 3, 6, negative 4. OA is 2, negative 1, 5. Find the difference of each component. 3 minus 2 is 1. 6 minus negative 1 is 7. Negative 4 minus 5 is negative 9. All right, there's our direction vector. So now in order to determine our vector equation, we have x, y, z. Okay, that is going to be the vector. I just need to start with one of my position vectors. I'm going to start with OA, 2, negative 1, 5. And I'm going to add some multiple of our direction vector, 1, 7, negative 9. And note that t belongs to the set of real numbers. There's a vector equation. Next step is a parametric equation, B. Parametric equation. So I just need to break this. I need to break this vector into its component parts. Okay, which means that I'm going to have x equal to 2 plus some multiple of 1. 2 plus, well, 1 times itself is itself, so just 1. It's just 2 plus t. Y is going to be negative 1 plus 7t. And z is going to be 5 minus 9t. Again, t belongs to the set of real numbers. I'm going to squeeze c down here. Basically, I'm going to test to see, determine, or answer the question, is c, point C at 0, negative 15, 9 on the line? Is that on the line? Okay, all that means is that I need to find out if I can build 0 from this x component of my parametric equation, and build negative 15 from my y component, and build 9 from my z component using the same t value. Okay, so in order to do that, we're just going to sub these pieces into our parametric equation pieces. So for our x component, I need to find the value of t that makes this true. That makes 0 equal this piece. Okay? Subtract t from both sides, I get t equals negative 2. Now I'm going to move on to my y component. Negative 15 has to equal negative 1 plus 7t. I'm going to add 1 to both sides. It's going to be negative 14 equals 7t. Divide both sides by 7. I'm going to get t equals negative 2. It's looking good so far, but confirming 2 parameters is not enough. So I'm going to look at my z. 9 equals 5 minus 9t. This one's pretty easy to see it's not going to work, because as soon as I add or subtract 5 to this, it's not going to be a multiple of 9 anymore. I'm going to subtract 5 from both sides. Get 4 equals negative 9t. Divide both sides by negative 9. I get t equals negative 4 over 9. The t values are not all equal. Therefore, c, 0, negative 15, 9, is not on the line. All right. There is one final note at the end of the lesson, and it basically says that if you have any line in two-dimensional space and you find a line that's perpendicular to it, then you know that any other line perpendicular to it is actually going to be parallel to any other line that is perpendicular to it. And you can do that. There's an infinite number of normals to the original line. Now, when you're in three-dimensional space, it is true again that there are an infinite number of normal vectors to a line, but they are not necessarily perpendicular to one another. Why is that? Well, because you might have one heading off in this direction, straight up, and you might have one heading off in this direction, straight down, or whatever direction that is. And they're all still perpendicular to the normal, but they might be heading, this way or that way or up or down. And so they're not necessarily parallel to each other in three-dimensional space, just something you need to watch out for. Your practice problems come from page 437. Page 437, and you are responsible for numbers 1 through 26. Thanks for watching.